This is Jane. Jane commutes to work every day and is a very safe driver, but today there was another driver on the road that was not so safe. Flash forward 2 weeks. Jane is completely recovered from her injuries. However, since the crash, she hasn't been able to get into a car without having intense feelings of panic, which has been interfering with her ability to get to work on time. Her sleep has also been interrupted by vivid and terrifying nightmares. A friend noticed these symptoms and pointed out that a nearby university was running an experiment about PTSD and motor vehicle trauma during which they would scan her brain using a thing called an fMRI. She would be shown some images and her brain's reaction would be recorded. So, what is an fMRI and how could it help Jane understand more about her emotional trauma from the car accident? In basic terms, an fMRI, or functional magnetic resonance imaging, is a method of diagnosing brain activity specifically by monitoring circulation of blood through different parts of the central nervous system. In this case, they would be looking at Jane's brain. As opposed to a regular MRI, which just creates images of soft tissue, functional MRI allows for experimenters to see how the brain reacts to presentation of different stimuli, in this case, pictures of car crashes. The magnetic field applied by the MRI scanner can be described using the Lorentz force law, which states that the magnitude of the magnetic field force is equal to the charge of the object passing through the field, Q, multiplied by the velocity of the object, V, which is then multiplied by the magnitude of the magnetic field, B. The readings of an fMRI are sourced from hydrogen atoms found in high quantities in the blood that circulates through the brain. Given that protons have a single proton as a nucleus, you can see from this equation that they would experience a force F from the magnetic field applied by the scanner. Chapter 38 in the Wolfson textbook, Nuclear Physics, provides the graphic above. A magnetic field, created by superconducting coils in the scanner, is applied to the patient's brain. Because of their charged proton nucleus, the hydrogen atoms in the blood align themselves with the magnetic field. Then, a certain radio frequency, 64 MHz for a clinical fMRI machine, is applied by the scanner's field-modifying coil, perpendicular to the magnetic field. You can see the orientation of these coils in the graphic from the textbook. The absorption of the radio frequency's photons causes the hydrogen atoms in the blood to jump to a higher energy state and then drop back, emitting energy until they eventually return to equilibrium. The MRI scanner's receiver coil measures the summation of this emitted energy and how it is dispersed across different areas of the brain. This can inform the clinician about patterns of brain activity. After signing some consent forms, it is time for Jane to get in the scanner. Next, she is shown images, some of which are of car crashes. It turns out that compared to healthy control subjects, she experienced higher brain activation in regions associated with stress after being shown the images of car crashes. These regions are known to be highly activated in subjects with post-traumatic stress disorder, or PTSD. So it was as Jane thought. She felt relieved to know that the fear she was experiencing was real. Afterward, she was paid for her time, and the doctor was able to recommend a therapist to help her with her symptoms. And for the first time since her crash, Jane felt optimistic again, and all thanks to the physics of functional magnetic resonance imaging.